Hello everyone, my name is Ramya. I'm a postdoctoral student working with Professor Gao at Stanford University. The topic of my today's presentation is on design and performance considerations for a lunar navigation and communication satellite system with a GPS time transfer. As we are all well aware, many efforts are being invested in designing a dedicated lunar constellation that can provide reliable navigation and communication services. In our work, we refer to this as Lunar Navigation and Communication Satellite System, in short known as LNCSS. Some examples include LunarNet, Moonlight, Andromeda, JAXA satellite system, and so on. Additionally, there is a growing interest in using small sats given their cost effectiveness and potential for rapid deployment. However, many design choices for LNCSS are not yet finalized, such as clock, constellation size, lunar orbit, and so on. In this context, NASA's Lunar Relay SRD and SCAWG reports identified the operability criteria for a small sat-based LNCSS. In particular, the near future criteria focused on the South Pole region, which is a key site given the presence of water ice deposits. We categorize these criteria into three: navigation service related, communication service related, and small sat factors. Firstly, under navigation service, the design criteria involves ensuring an adequate accuracy of user position and receiver clock timing. Breaking it down further, this service reliability depends on different metrics, of which the key ones are listed here. First is lunar user equivalent ranging error or UERE, which determines the signal ranging accuracy. Next is geometric dilution of precision or GDOP, which depicts satellite geometry with respect to user. Then the others are service availability, coverage, and failure tolerance. Note that navigation availability requires at least four visible satellites, while failure tolerance metric requires a minimum of five. Secondly, under communication service, the design criteria involves ensuring sufficient daily volume of data transfer to and from Earth. This in turn depends on different performance metrics, of which one is the rate of data transfer between lunar user and Earth. Other metrics for communication include service availability, coverage, and failure tolerance. In contrast to navigation availability, communication availability requires at least one visible satellite, while its failure tolerance metric requires at least two. Finally, the performance metrics related to small sat factors are listed in this table. First is overall constellation cost. The others are size, weight, and power or SWAP, which limits the onboard equipment, and delta V for station keeping, which depicts maneuvers required to maintain orbit stability. Note that the focus of this work is on assessing which design considerations influence satellite level and constellation level design choices, whereas accounting for some of the other factors such as hardware design or lunar user burden will be explored in our future work. This slide tabulates some amazing prior works that exist on lunar constellation design. To identify the research gap, we assessed existing literature based on whether they satisfy the design criteria and performance metrics of navigation and communication services and also small sat factors. Here, orange represents that the preliminary requirements outlined by NASA are not addressed, yellow implies partially addressed, and teal is fully. We can see that in the context of small sats, majority of these works either focus on navigation or communication. Given this, the focus of our work is on jointly investigating the navigation and communication considerations specifically for designing a SmallSat-based LNCSS. To account for SmallSat constraints, in our prior works, we designed a time transfer architecture that harnesses the weak Earth GPS signals to alleviate requirements related to timing stability and grade of satellite clocks. An illustration of this concept is shown over here. More specifically, we designed a timing filter that estimates clock corrections when Earth GPS signals are available. We also devised a lunar UERE metric that depends on the filter estimation error, and demonstrated its estimated value to be comparable to that of Earth GPSs even with a CSAC. In this work, we conceptualize a small SAT-based LNCSS architecture that jointly provides both navigation and communication services at lunar South Pole. We leverage time transfer from Earth GPS for improving navigation ranging precision and communication time sync. As illustrated in this figure over here, we intelligently designed a hybrid constellation type wherein all satellites are enabled with navigation services, while only a few of them provide communication services. We designed various LNCSS case studies based in ELFO and CSAC and analyzed their trade off in terms of design criteria, performance metrics, and small sat factors. The outline of the presentation is seen in this slide. I will first explain the design and performance considerations of our LNCSS concept. Next, I will analyze the trade-off across various case studies using simulated experimental data. In the end, I will summarize my talk. First, let's look into our LNCSS design considerations, starting with navigation service related. The navigation design criteria, which involves achieving adequate accuracy of positioning and timing, mathematically depends on the product of lunar UERE and GDOF. The other three performance metrics over here influence when and where the navigation services are available, which essentially depend on the number of visible lunar satellites over the South Pole region. Now let's dive a little deeper into how Earth's GPS time transfer influences this lunar UERE metric. Our prior works go into a detailed breakdown of lunar UERE, wherein we essentially utilize the fact that unlike Earth, Moon does not have atmosphere or buildings. So, as shown in this equation over here, the error sources of lunar UERE that are included in this lunar UERE are broadcast clock, group delay, broadcast ephemeris, and receiver noise. More specifically, the broadcast clock component depends on time corrections estimated using Earth GPS time transfer. Note that compared to our prior works, in this work, we designed a three-state Kalman filter that accounts for nonlinearities by estimating the clock drift rate in addition to clock bias and drift. Now, coming to communication service performance, the design criteria involves ensuring sufficient daily volume of data transfer to and from Earth. As shown in this figure, the daily volume involves data transmitted across two segments. One is between user and lunar satellite, and the other is between satellite and Earth. Based on the frequency band allocation, the first S segment involves S-band communication, whereas the second K segment considers K-band. Mathematically, our daily volume is minimum between the data transferred in both segments. In each segment, the transmitted data is computed as a product of the data rate and visibility duration of the lunar satellite. Now, let me explain how we calculate this data rate. As shown over here, data rate depends on received signal power, signal to noise ratio, and other hardware terms like transmitter and receiver gains. Among them, the received power depends on frequency and max communication distance in that segment. Mathematically, the signal to noise ratio depends on bit error rate, which in turn depends on filter estimation error from our Earth GPS time transfer. So essentially, our Earth GPS time transfer affects both lunar UERE and data rate, and which in turn influences both navigation and communication design criteria. Within SmallSat factors, delta V is specific to the lunar orbit chosen, whereas cost, size, weight, and power are computed heuristically for the space segment. In essence, the space segment cost is divided into total development cost and total production cost. We compute these costs specific to our hybrid constellation design, which is shown in this figure on the left. In particular, we break down the development cost and production cost into communication payload and nav-only satellite, which can be seen here, 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 and here. Note that the development cost depends on mass, whereas the production cost depends on the first unit cost and the number of units to be produced. Let's look at the development cost in more detail. Starting with communication payload, its development cost depends on its mass and number of communication channels. The mass of this communication payload in turn depends on the number of antenna and their respective diameter. Note that a minimum of two antennae are required, one to point towards Earth and the other to point towards the lunar user. Also, another point to note is that these functions are heuristically computed, derived from Space Mission Engineering textbook, which is referenced in this slide over here. In contrast, we will use a different approach to compute the mass of navigation-only satellite, which will be used to compute its development cost. First, we compute the total payload power by summing the power of individual payload components as shown over here. Then we utilize the data from past missions to heuristically compute the mass given the total payload power. In this table, pay special attention to the small sat components wherein we are using a lower grade CSAT and along with an Earth GPS receiver to maintain onboard timing stability. Now, I will talk about our simulated experimental results that analyze the trade-off among different LNCSS case studies. To eliminate the station keeping needs, we considered an ELFO-based flower constellation setup. We designed 3 case studies, A, B, and C, that involve 8 satellites, 12, and 16 satellites. We evaluate them against criteria outlined in NASA reports and few other sources. Across all case studies, the mean anomaly and RAN are chosen to evenly distribute the satellites, whereas the other orbital elements are chosen to maintain frozen orbit conditions. As highlighted by orange-colored satellite in these figures, we also implement our hybrid constellation design by considering only 25% satellites to provide comm services. We utilize SDK software to model Earth GPS, LNCSS, and lunar users. As shown over here, we perform exhaustive analysis of the lunar constellation operability by considering a total of 334 users that are uniformly spread over southern latitudes greater than 80 degrees. We also analyze 2 elevation mask angles. One is 5 degrees that represents open sky condition and 20 degrees for mimicking the restricted availability in craters. In the first set of results, we assessed our Earth GPS time transfer by considering a CSAC. Based on this, the onboard timing accuracy is 8 nanoseconds, which satisfies the recommended NASA SRD limit of less than 20 nanoseconds. Also, our lunar UERE is estimated to be 3.86 meters. And our estimated data rate is 44.7 Mbps, which also falls within the specified range of 5 to 100 Mbps. In the second set of results, we compare navigation design performance across all case studies for an elevation mask of 5 degrees. We can validate that even during single satellite failure, both cases B and C satisfy a NASA requirement of at least 98% navigation availability. Over here, we can demonstrate that case C satisfies NASA's recommended 1 sigma position accuracy of less than 10 meters and also global exploration community's prescribed accuracy of less than 50 meters. Also note that all these case studies satisfy receiver timing needs with accuracies less than accuracies up to 1 microsecond. Now let's zoom in on case C and analyze its performance for higher elevation mask of 20 degrees. This figure on the left demonstrates the heat map of GDOT, which ranges between 5.9 in blue to 7.3 in yellow. Comparing the position and timing accuracies across elevation mask angles, we can demonstrate that even for higher elevation mask, case C still satisfies the global exploration community's desired position accuracy of less than 50 meters. Now let's look at the communication performance comparison. for elevation mask of 5 degree. Based on the values over here, we can observe that the failure tolerance for cases A and B with fewer satellites is lower than case C, which maintains 100%. Nevertheless, we can observe that both cases B and C satisfy high data rate requirement of 75% communication availability. Also, we can observe that the daily data volume across all case studies satisfy desired values taken from different sources, that is greater than 160 GB, between 240 to 2400 GB, or 600 GB. Now, let's take a closer look at case C's performance for a higher elevation mask angle of 20 degrees. This figure on the left demonstrates the heat map from the S-band segment, which indicates that the minimum visibility duration of a lunar CommSat is around 14 hours. Comparing the minimum of S and K segments, we can achieve daily data volumes greater than 1000 GB for both elevation mask angles. Based on this, we can demonstrate that case C satisfies the recommended communication design criteria. Finally, let's compare space segment costs across all case studies. For this analysis, our estimated heuristic mass of navigation-only satellite is 133 kilos, and estimated mass of navigation and communication-enabled satellite is 158 kilos. We can observe that both these mass values fall within the small sat constraints. This table shows the development cost, production cost, and the total space segment cost across all case studies. Based on this last column over here, the average satellite cost across all case studies is computed to be less than $17 million, and this is comparable to NASA's low-cost capstone mission that was recently launched in June. To summarize, in this work, we analyzed design and performance considerations for a SmallSat-based LNCSS to provide reliable navigation and communication services at lunar South Pole. We also performed high-fidelity SDK simulations and examined 3 case studies in ELFO using a CSAT based on our Earth GPS time transfer architecture. We also performed trade-off analysis in satisfying the design criteria listed in NASA SRD and SCAWG reports. We want to thank AGI Educational Alliance Program for providing us with the SDK software license. We also want to thank members of NAVLab for their insightful discussions. Thank you.